Well, hello there, Internet. This video is going to show you how to do calculations in a basic inclined plane problem. So we have a 5 kilogram cart. It's frictionless in this situation. Right now it's tied to a wall that's preventing it from rolling down that 30-degree incline. So the first thing we're going to do is we're going to calculate how much tension is in that string. So of course, we're going to start with a free body diagram. Force of gravity always points straight down toward the center of the earth. It doesn't matter that it's on a tilted surface, gravity is going to point straight down. I always look for contact points. Anywhere there's a contact point, there's going to be a force. So one contact point is where the string touches it. So let's draw that force in. The force that a string exerts is always in the same direction as the string. Strings only ever pull, they don't push. And we call that tension force. Then we have the wheels in contact with the inclined plane. And the electrons of the inclined plane are going to repel the electrons of the wheel. That repulsion is going to be directly away from the inclined plane. So it's actually in this direction. It is not straight up. And we call that force normal force. Normal force is always perpendicular to the surface that's exerting it. And there could be friction at that contact point between the wheels and the ground, but I'm making this problem a frictionless problem. So really, that's it. Gravity, your two contact points, that's what your free body diagram looks like. And by the way, I'll just note that when we cut the string and it accelerates, it's going to accelerate that way. Now, that's not part of my free body diagram. You shouldn't draw anything other than forces on your free body diagram, but I just wanted to point that out because a typical way you might solve a problem like this, if you didn't know any better, this is going to be wrong, so don't follow what I'm doing, is to make your x and y axis like that, horizontal and vertical. The problem with this is you're going to have to find the x and y components of tension, which is unknown, the x and y components of normal force, which is unknown, and the x and y components of acceleration, which is unknown. That's three unknowns on each axis, and that just makes it mathematically virtually impossible to solve this problem. So I'm going to use a little trick that you should always use. Not just, I was going to say with inclined plane problems, not just with inclined plane problems, but with any problem. And that trick is you can tilt your axis, and you always want to tilt your axis so that acceleration is parallel to one of the directions. So I'm going to tilt it like this. The reason that's so important is because, first of all, we're not going to have x and y components of acceleration. And secondly, one direction of acceleration, in this case right here, is going to be equal to 0, and it'll make our equations easier. So always tilt your axis so that acceleration is parallel to one of the directions. Now, what we are going to have to do is find the x and y components here of the force of gravity. So let me draw those in there. Remember, you're going to drop your perpendicular. You want it to be perpendicular to the axis, not perpendicular to the force of gravity. So see that little 90-degree angle there. That shows me that my y component looks like this, and my x component looks like that. Now, the force of gravity here, we can use our basic force of gravity equation, which is m times g. The mass is 5 kilograms. G is 9.8 newtons per kilogram on Earth. That gives us 49 newtons. So the hypotenuse of this triangle is 49 newtons. We need an angle to know how to proceed and to proceed correctly. So I'm going to find that angle right there. And to do that, let me just redraw our car a little bit bigger. So here's our car. Here's our inclined plane. And let me redraw a couple other things. Here's the force of gravity. Here's my tilted y-axis. So I'm interested, I know I was given that this angle is 30 degrees. Well, the angle between gravity and the horizontal is going to be 90. So this is a right triangle, and this with a double angle line is definitely a 60-degree angle. Now, across from that over here, vertical angles are congruent, so that's also a 60-degree angle. Where my tilted y-axis meets my tilted surface, that's a 90-degree angle because my x-axis is parallel to that surface, which makes this in here a 90-degree angle, and that right there, since that's 60, that has to be 30. So this angle that I've identified right there, that is a 30-degree angle. And here's a little hint for the future. It turns out that the angle between the force of gravity and the axis that is perpendicular to the incline, typically you'd call that the y-axis, is always going to be the same as the angle between the incline and the horizontal. So I'll say that again. The angle between the force of gravity and the axis that is perpendicular to the incline will always be the exact same angle as the angle between the incline and the horizontal, which in this case is 30 degrees. So you don't really need to draw a picture like that every time. You can just kind of remember that. So now we can get down to business with finding our components. This component right here, the y component, is adjacent to that 30-degree angle, so I would use cosine. Cosine of 30 is equal to adjacent over hypotenuse, which is 49. So adjacent equals 49 cosine 30, and according to my calculations, that is 42.4 newtons, 42.4 newtons. Let's take a look at the x component, which is opposite the 30-degree angle. So I will use sine. Sine of 30 equals opposite over hypotenuse, which is 49. So opposite equals 49 times the sine of 30, and that's equal to 24.5. So that is my x component of gravity. Now we're ready to write a Newton's second law equation, one for the x direction and one for the y direction. So here's the x direction. Acceleration in the x direction is equal to the forces in the x direction divided by the mass. Now the forces in the x direction, you know what? I was about to say there's only one, but hey, guess what? There's two. We have the component of gravity that we just figured out that points down the incline. So I'll make it negative because it points to the left. Is 24.5, negative 24.5. Then we do have the tension force, which is positive tension force. And so that's going to be the equation for the x direction. So how about the equation for the y direction? We have the normal force, which is positive. And then we have the component of gravity in the y direction, which points down our tilted y-axis. So that's going to be negative 42.4 newtons. And that's divided by the mass. Okay, so what can we figure out here? Well, we can answer the question about the tension force by recognizing that since the string is holding it in place, the acceleration is 0. So 0 equals negative 24.5 plus Ft divided by 5. You do the math on that, and you're going to find out that tension is equal to 24.5. So no surprise here, the tension force is just equal to the component, the x component of gravity, which is trying to pull it down. Tension is balancing that out, so it stays at rest. How about the normal force? Well, you know, in the y direction, the acceleration is also 0 for two reasons. One, it's not accelerating up off the incline or down into the incline. And two, remember, we tilted our axis so that even when we do have acceleration, the y direction is perpendicular to that. So there's 0 acceleration in the y direction. So that's going to be positive Fn minus 42.4 newtons divided by 5. So the normal force is just simply equal to 42.4 newtons. I didn't ask you to do that, but it's good to see that. Okay, how about if we cut the string? What is the acceleration going to be? Well, I can use the exact same equation here, except now I'm trying to find an unknown acceleration. The x component is still negative 24.5, but if I cut the string, you know what? There's no tension, or you can say that the tension is 0. But literally, there's no tension force if I cut the string. We still have 5 kilograms over here. So that's going to give us an acceleration in the x direction of negative 4.9 meters per second squared. And the negative there, of course, just indicates direction. It indicates that it's going to accelerate in what we are calling the negative direction, which is down the incline, and that makes sense. All right, so good luck with your inclined plane problems.